This lesson discusses graphs of equations in two variables as well as intercepts and symmetry. So first here, definition, the graph of an equation in two variables, x and y, consists of the set of points in the xy plane whose coordinates x, y satisfy the equation. So the coordinate pair will satisfy the equation if it lies on that line or that graph, whatever it may be. So this example will determine whether the points are on the graph of the equation 2x minus y equals 6. We're just going to take those ordered pairs and plug them into that. So 2 times 2 minus 3, does that equal 6? That's 4 minus 3. 1 does not equal 6. So the point 2, 3 does not lie on the graph of that equation. For b, same thing, plug it in. 2 times 2 minus negative 2, does that equal 6? That would be 4 plus 2 equals 6. 6 does equal 6. So this one is on the graph. Okay. We're now going to graph the equation. These ones we're going to do by just plotting the points. So first we have y equals 2x plus 5. We know it's a linear equation because its highest degree is 1 on the x term there. So we can just kind of pick any 2 points. I'm going to pick 3 just to be safe here, but say for example if we let x equal 0, we plug in 0 for x, so 2 times 0 is 0 plus 5 would equal 5, so the ordered pair point on the graph would be 0, 5. I'm going to try x equals 1, so 2 times 1 plus 5, 2 plus 5 is 7, so the ordered pair would be 1, 7, and say maybe I try negative 5 for x. Plug in negative 5. That's negative 10 plus 5, which is negative 5, so the point negative 5 would be on the graph, and we can plot those. So 0, 5, 1, 7, and negative 5, negative 5. And then you can connect those to make a straight line. And we said that one was linear. Next, graph the equation by plotting points y equals x squared. This is the parent function of a parabola or a quadratic function. So with this, we have, it's not just a straight line. So it's kind of always helpful just to pick, maybe test 0. Symmetry is going to come into play and be very helpful here later on in this lesson, but this is the most basic parent function of the quadratic. So let's try when x equals 0. Then y equals 0 squared, which is 0, so the point 0, 0 is on the graph. Now, that's going to be our turning point, and we'll see that here. When you're plotting points to graph parabolas, you want to plot where it turns, and you also want to plot a point on each side of that. So since x equals 0 is where it turns, we're going to try when x equals, let's try negative 2 and positive 2. So this would be 2 squared, which is 4. So the point 2, 4 is on the graph. Negative 2 squared is also 4. So the point negative 2, 4 is on the graph. And just for good measure, I'm going to do 3 and negative 3 as well. 3 squared is 9. So the point 3, 9 is on the graph. Negative 3 squared is 9. So the point negative 3, 9 is on the graph. So let's go ahead and plot those. 0, 0. All right, right, so we have our parabola here. It's our U-shaped graph. This stems from a quadratic equation. It's called a parabola. All right, so we'll talk about symmetry here, but you can see it's the same on both sides of that axis of symmetry I just drew. All right, so let's look at intercepts next. The points, if any, at which a graph crosses or touches the coordinate axis are called the intercepts. So the x-intercept or intercepts crosses or touches the x-axis, and the y-intercepts will cross or touch the y-axis, as shown there in that picture. So it does not have to cross all the way through. It can just touch it and turn back the direction that it was going. Examples here, find the intercepts of the graph. So we have our x-intercepts, or where it touches or crosses the x-axis. So in this case, that's going to be negative 4, 0, and 3, 0. The y-intercepts is going to be where it crosses or touches the y-axis. So here we just have 1 at 0, negative 3. So all of those are intercepts, and then specifically you have your x-intercepts and your y-intercepts. So you can find intercepts by looking at the graph, or in this next example, it says find the intercepts of the equation y equals x squared minus 4. We can also do it algebraically. So to find intercepts from an equation, to find the x-intercepts, you're going to plug in 0 for the y value, because x-intercepts are where it crosses the x-axis, which is where y is 0. And then for y-intercepts, you're going to plug in 0 for x and solve for y, because on the y-intercepts are where it crosses the y-axis, and that is when x is 0. So think of maybe plugging in 0 for the opposite variable of the intercept you're trying to find. So an x-intercept, you're going to plug in 0 for y. So 0 equals x squared minus 4. We now need to solve for x. I'm going to add 4. So 4 is equal to x squared. We're going to take the square root of both sides. Remember, when you take the square root of a number, the answer is really the positive and negative of whatever the square root is. So our x-intercepts are 2, 0, and negative 2, 0. Our y-intercepts, we're going to plug in 0 for x, so y equals 0 squared minus 4, so y equals negative 4. So our y-intercept is 0, negative 4. So notice for my y-intercept, my x is 0. For my x-intercept, my y value is 0. And it says now graph the equation by plotting points. If you have the intercepts, it is easiest to just plot the intercepts. And then if you have to plot additional points, you can determine if you need to from there. But let's just plot 2, 0, negative 2, 0, and 0, negative 4. So again, there we have a parabola where its turning point is at 0, negative 4, or its vertex. Okay, moving on to symmetry. So symmetry in math is just like it's always been in art and math growing up. It's where something is this exact same on one side of some imaginary line drawn. So here we're going to match each graph with its type of symmetry. So with respect to the x-axis, that means it is the same, it looks the same, reflected across the x-axis. So the one that matches up with that would be our middle graph there. So notice what was an x and y coordinate became an x and a negative y coordinate. So the y coordinate becomes negative. Symmetry with respect to the y-axis, that means it reflects over the y-axis, which matches up with our last one here. So notice an xy coordinate becomes negative xy. So the x coordinate changes when you're reflecting it across the y-axis, which is how we're getting that symmetry. And then last, symmetry with respect to the origin, or the point 0, 0, would be this first one. And both x and y values are being negated. So an x, a y value, if it's symmetrical, there will also be the point negative x, negative y. So we can test equations for symmetry without looking at the graphs. We're going to do a little bit of both here. So test for symmetry here. For the x-axis, replace y by negative y in the equation and simplify. If it's the same exact equation as what it originally was, then the equation is symmetric with respect to the x-axis. Testing for symmetry with respect to the y-axis, we're going to replace the x by negative x in the equation. And if that equation is equivalent to the original, then it is symmetric with respect to the y-axis. And then for the origin, we're going to replace x by negative x and y by negative y in the equation. And if it's equivalent to the original equation, then it is symmetric with respect to the origin. So let's take a look here. With respect to the x-axis, we plug in the opposite of y and simplify. So 4x squared plus 9 opposite of y squared equals 36. If I simplify that, I get 4x squared. Negative y squared, a negative squared always becomes a positive, so this becomes plus positive 9y squared equals 36. That's the exact same equation as the original, so this equation or graph is symmetric with respect to the x-axis. All right, we're going to do the same thing with the y-axis, except for now we change the x to a negative x. So 4 times negative x quantity squared plus 9 y squared equals 36. Simplify that, you have this similar situation. Negative x quantity squared becomes a positive. So 4x squared plus 9y squared equals 36, which is the same as the original. So this graph is symmetric with respect to the y-axis. And then last here we have with respect to the origin, and to figure that out we're going to plug in opposite of x and opposite of y. So 4 times negative x quantity squared plus 9 times negative y quantity squared equals 36. That becomes 4x squared plus 9y squared equals 36, which matches the original. So this graph is also symmetric with respect to the origin. So it has lots and lots of symmetry because this is the equation of, it's an ellipse. All right. Doing the same thing for this next one. Very, very similar, so I'm just gonna kind of go through it quick. With respect to the x-axis, I'm plugging in opposite of y equals 4x squared over x squared plus 1. If I divide by negative 1 on both sides, that is what I come up with. That is not the same as the original, so it is not symmetric about the x-axis. Y-axis, I'm going to use the opposite of x. And if I simplify that, I get y equals 4x squared over x squared plus 1. And that is the same as the original equation. So this equation is symmetric with respect to the y-axis. And let's check for the origin. I'm negating both of them, so negative y equals 4 times negative x squared all over negative x squared plus 1. Well, we know that right-hand side becomes the original. So we have negative y equals 4x squared over x squared plus 1. And if we divide by negative 1, this is what we got the first time. So this graph is only symmetric with respect to the y-axis. All right. Graphing key equations here. So we're going to be using that symmetry along with intercepts and plotting points to graph our equations here. So we have y equals x cubed. We're going to start with the x and y intercepts. We can find the x-intercept by plugging in 0 for y. So 0 equals x cubed. If you take the cube root of both sides, you get x equals 0. So the x-intercept is at 0, 0. The y-intercept, we're going to plug in 0 for x, so y equals 0 cubed, which is 0. So the y-intercept is also 0, 0. Symmetry-wise here, with respect to the x-axis, negative y equals x cubed, so y equals negative x cubed. That is not the same as the original, so there's no symmetry with respect to the x-axis. With respect to the y-axis, we're going to do y equals negative x cubed. A negative to an odd power stays negative, so y equals negative x cubed, not the same as the original. So now we check for the origin, negate both of them, so negative y equals negative x cubed. That's negative y equals negative x cubed, and if you divide by negative 1 on both sides, the negatives cancel out. So y equals x cubed is the same, so there is symmetry with respect to the origin. Okay, so now we can plot some points. Well, first of all, since we know that there's symmetry with respect to the origin, whatever x, y values we get, if we just negate the x and the y, then we'll have more points to plot. So since it's symmetrical with respect to origin, then any xy value we get, we can also use the negative x, negative y value. So we know 0, 0. So if x is 0, then we know y is 0. So the point 0, 0 is on there from our intercepts. And then I'm gonna pick points in the first quadrant. So let's say if x is 1, then 1 cubed is 1, so that means y is also 1. So the point 1, 1 is on there. And then let's do if x is 2. 2 cubed is 8, so the point 2, 8 would be on there. So that also means the point negative 1, negative 1, and the point negative 2, negative 8 are on there. So we are going to plot all of those. 0, 0, 1, 1, 2, 8, and then negative 1, negative 1, negative 2, negative 8. So here is what a cubic function looks like. All right, we can do the same thing with the next two, but I went ahead and put here, let's take a look at these on Desmos. We have x equals y squared. Graph the equation, find any intercepts, and check for symmetry first, and then graph the equation where only y is greater than or equal to 0. And then we will graph the equation 1 over x. So let me see. All right, so first we have x equals y squared. And then we're going to want to see it where y is greater than or equal to 0. I don't know. Oops, okay. All right, so there's our x equals y squared graph there. You can see there's one intercept at 0, 0, and it's symmetrical with respect to the x-axis. If we're to graph it when just y is greater than or equal to 0, then it's only going to be what's in the first quadrant. Okay, so what's in the fourth quadrant right now is y is less than or equal to 0. So it actually ends up being the same equation as y equals the square root of x. Okay, so where my green is there, when y is greater than or equal to 0, it's the same equation as that. So, oops. Let's just write some things down quick. Intercept at 0, 0. Symmetric with respect to x-axis. And some of those points when it's greater than 0 would be 0. Y is greater than or equal to 0, 0, 0, 1, 1, 4, 2, and so on. So if we graph those, it looks like that. And then our other half was like so. And then last here, graph the equation y equals 1 over x. So if we just do 1 divided by x, it looks like this. So you can see there are no intercepts at all. Okay, it never crosses the x or y. It looks like it's touching it, but it never is. And there is symmetry, and it's across the origin. So you should see, like here, this point here, the point 2, 1/2. There's also the point -2, -1/2. So both the x and the y became negative. So that shows our symmetry in the with respect to the origin. So this one has no intercepts. Symmetric with respect to the origin. And some of those points were 1/2, 2 we mentioned, which means there was also -1/2, -2. 1, 1 was a point, so -1, -1's a point. And 2, 1/2 was also a point, so -2, -1/2 is a point. And if we graph those here quickly, 1/2 is kind of hard to get on here. So 1/2, 2, 1, 1, 2, 1/2. Looks like that. And same thing in the third quadrant, -1/2, -2, -1, -1, -2, -1/2. And there you have it.